If a fluid begins perfectly smooth, can its motion become infinitely violent in a finite amount of time? Can a tiny vortex stretch, accelerate, and collapse until its rotation reaches infinity? Nobody knows. The equation behind this mystery describes currents in the ocean, storms in the atmosphere, air moving around an aircraft, blood flowing through an artery, and the chaotic motion we call turbulence. Engineers use it every day, yet after more than 200 years, mathematicians still cannot prove that a smooth flow always stays smooth. Solving this problem is worth $1 million. Welcome to Data Alchemist. 6 Millennium Prize problems remain unsolved. The Riemann hypothesis, P versus NP, Yang-Mills and the mass gap, the Hodge conjecture, Birch and Swinnerton-Dyer, and Navier-Stokes. Each has $1 million prize. Each hides a different limit of human knowledge. In this episode, we are following the fluid. Navier-Stokes asks one precise question. If a fluid begins perfectly smooth, must it stay smooth forever? Or can some velocity gradient or rotation become infinite in finite time? Either answer wins the prize. Nobody has proven either one. Before Navier-Stokes, mathematicians imagined fluids with no internal friction. Leonhard Euler's ideal fluid. Nothing slows it down. Real fluids resist. In 1822, Claude-Louis Navier added friction between sliding layers. In 1845, George Gabriel Stokes rederived the same friction independently from a more rigorous continuum framework. 2 centuries, one equation built in layers. Start with Newton's law. Force equals mass times acceleration. Now shrink that mass down to a tiny piece of fluid. Local acceleration, how the velocity at one fixed point changes in time. Nonlinear transport, the fluid carries its own velocity along with it. This is the term that makes the equation genuinely hard. Pressure pushes fluid away from itself. And viscosity, a sharp spike, blurred smooth. Friction, fighting sharp edges. One more rule, quietly enforced. Squeeze it here and it bulges there. Volume never changes. One law, 5 terms, one unanswered question. Vorticity is just local spin. Write down how that spin changes in time and one term stands out, vortex stretching. Picture a skater, arms out. Pull the arms in and the spin speeds up. Same idea in a fluid. In 2 dimensions, a vortex can't be stretched like that. The dangerous term is exactly 0. In 3 dimensions, it isn't. A vortex tube can thin out and spin faster and faster. Nobody has proven that viscosity always wins that race. A strong solution is a perfectly sharp picture. A weak solution may have some damaged pixels, but viewed through every smooth blur filter, it gives back the same answer. In 1934, Jean Leray proved that a global solution always exists. He did not prove it stays perfectly smooth. That gap sat quietly for 66 years, until the year 2000, when the Clay Institute made it official. Poincaré's conjecture was solved in 2003. Navier-Stokes is still waiting. In 2025, researchers at DeepMind did not solve Navier-Stokes, but they found something mathematicians had struggled to pin down: unstable blow-up shapes in closely related fluid equations. Here's the problem. A simulation chasing one of these shapes is like a marble balanced on a narrow 3-dimensional ridge. It must follow the ridge perfectly as the length scales shrink and the gradients grow. One tiny numerical or round-off error and it falls away from the singular path. The trick is to stop chasing the explosion and instead zoom in at exactly the rate it's exploding. In those rescaled coordinates, the sharpening peak holds still. It becomes a fixed shape. Now comes the AI part. A neural network represents a candidate profile, u theta. Automatic differentiation calculates the profile's derivatives, and the candidate is substituted directly into the rescaled fluid equation. Wherever the two sides disagree, the residual lights up. Training adjusts the network until that error becomes small across the whole domain. This is a physics-informed neural network, or PINN. It is not mainly learning from a collection of previous vortices. The differential equation itself becomes the teacher. The physics applies the training signal. I will explain pins step by step in a separate video. For this story, remember the essential loop. Propose a shape, differentiate it, measure the equation error, and refine the shape. The 2025 framework strengthened that loop with multi-stage refinement and a high-precision Gauss-Newton optimizer. This is not Navier-Stokes solved. It's a new way to search for the shapes that might matter. A marble in a bowl, nudged, rolls back to center. That's a stable shape. A marble on a ridge, nudged, falls a new way every time. That's unstable. Some of these blow-up shapes have one unstable direction. Some have two. Some have three. Each one another way for the shape to slip away from a simulation. So what would an actual answer mean? If smoothness is proven, this equation never breaks down. Turbulence stays hard to predict either way. If a blow-up is proven, somewhere, a perfectly smooth fluid stops being smooth. Your weather forecast keeps working regardless. Watch the tube collapse, thinner, faster, toward a single point. That point could be a question mark, or it could be $1 million, 2 centuries, one equation, one open question. Maybe the answer starts as a theorem. Maybe it starts as a shape a neural network finds first. Thank you for watching. Subscribe and stay curious about the open problems.